Welcome back to another new chapter within geometry. Today we are going to be starting chapter 5, which deals more with triangles. And just as a precursor, as a reminder, if you have questions on anything, my office hours are every single day from 11 to noon, and you can feel free to swing by. We're going to do this chapter and one more chapter to round out the year. But I really enjoy this chapter, and it's something that really solidifies some concepts that we've developed already in the previous chapter. And so today what we're going to discuss is something called the sine and the cosine ratios. And from last chapter we developed something called the tangent ratio. And so where we're going to begin today is actually in the streets of San Francisco. And it says, while traveling around the beautiful city of San Francisco, Juanita climbed several steep streets. One of the steepest is Filbert Street, which is an actual street that I've been there, and it winds back and forth in order to kind of make up for all the steepness of it. It has a slope angle of 31.5 degrees, and so it looks something like this. Once Juanita finished walking up 100 feet up the street, she decided to figure out how high she had climbed. She drew this diagram, change in y over change in x. And her question is, can the tangent ratio be used to find the change in y? And so she's trying to determine this, and with her given information in her right triangle, the question is, can we determine that? And the answer is no, we cannot. And the reason being, because we do not have either this side length, the change in x, or the change in y. What we have in this case is the hypotenuse. And so if we have the hypotenuse length, but neither of the other two legs of the right triangle, this is a situation that we haven't encountered yet using ratios of side lengths. And so that's what we're going to lend ourselves to today. So no, we cannot use the tangent ratio, just to summarize in this problem, because we have two unknowns in our legs of the change in y and change in x. Alright, now in order to determine how high Juanita climbed in problem 5-1, we need to know more about the relationship between the ratio of sides of a right triangle and the slope angle. And so it says in part A, use two different strategies to find the change in y for the slope triangles shown at the diagram at the right. Looking at this first triangle over here, the smaller one, if I were to try and determine this length, the change in y, I could actually use a Pythagorean theorem. That would be my first thought. I could do 1 squared plus y squared equals 2 squared, because I have a right triangle and I know two of the side lengths and not the third. So if I were to continue to solve that, I would get 1 plus y squared equals 4. Then I'd get y squared equals 3 by subtracting 1 from both sides. And then y would be equal to the square root of 3, because I'd have to take the square root of both sides. And doing the square root of 3 is approximately 1.73. So I could find that this side length right here, this vertical distance, is 1.73. I could additionally do the exact same process to determine this length right here. But what I could also notice is that these two triangles are similar to one another. This angle down here is a 60-degree angle, as is this one. And so I also have two 90-degree angles, so these triangles are similar by angle. So the scale factor going from this triangle to this one is multiplying by 3. Notice to go from 2 to 6, you're also multiplying by 3. So if I wanted to go from this side length to this vertical distance here, I would also multiply it by 3. So this side length, the change in y in the bigger triangle, would be equal to taking the smaller triangle, which is the square root of 3, and multiplying that by 3, or 1.73 times 3, which is going to be equal to 5.2 units to be able to determine that vertical distance on those triangles. It says find the ratio for the change in x over the hypotenuse for each triangle. Why must these ratios be equal? So looking at question B, that's what I'm answering right now. The change in x in both triangles, well, in the smaller triangle that would be 1 divided by the hypotenuse, which is 2. And then in the bigger triangle, that would be 3 divided by 6. And so hopefully we can recognize that that ratio is 0.5 for both of the triangles. Why must these be equal to one another? Well, similar triangles have equivalent ratios of corresponding sides. So the ratio of this short side length to the hypotenuse needs to be the same as this short length to the hypotenuse, as we have corresponding sides have the same scale factor. So it says here in part C then, find BC and AC in the triangle at the right. So in this picture, all I have is a 60-degree angle and a side length of 7. Well, based off of the work that we just did in the last problem, parts A and part B, what we can just recognize is, well, hey, we have this scale factor, the relationship of the short side length, the change in x, divided by the hypotenuse, which in this case is 7, and we know that that needs to be equal to 0.5, as we saw in these previous two problems. Well, what number divided by 7 is 1/2, or what's half of 7? That would have to be 3.5. So this length of BC is 3.5 units because the ratio of this short leg, change in x, divided by the hypotenuse, 7, is 3.5 out of 7, or 0.5. Then we can also use the fact that this triangle is similar to the other two because I have a 60-degree angle and a 90-degree angle. And so if I wanted to determine this long length right here, what I can do is I can take the length square root of 3, and instead of multiplying it by 3 this time, I'm going to multiply it by 7. And when I do that, the square root of 3 times 7 is going to turn out to be 6.06 units in length. So what we just discovered is a new ratio that we are going to ask that you write down, a very important ratio indeed. And so that ratio that we just discovered is called the sine ratio. It says in problem 5.2 you use a ratio that included the hypotenuse. There are several ratios that you might have used. One of them is the sine ratio, pronounced sine. This is the ratio of the length of the opposite side and the hypotenuse. And so for the triangle that is shown at the right, the sine of this 60-degree angle is the ratio of the opposite side length divided by the hypotenuse length. In addition to that, there's another ratio that we can use, which is called the cosine ratio. And so we have the sine and the cosine ratio. The cosine ratio is the ratio of the side length that is adjacent or next to your angle divided by the hypotenuse. So both the sine and the cosine use the hypotenuse. One of them just includes the opposite in the hypotenuse, that being sine, and the other one would be the adjacent leg in the hypotenuse, which would also be sine. In part A on this problem right here says, like the tangent ratio, your calculator can give you both the sine and the cosine ratios for any angle. And so that's a very convenient thing. And so it says, locate the sine and cosine buttons on your calculator and use them to find the sine and cosine of 60 degrees. Does your calculator give you the correct ratios? Yes, it should. Okay, just like we did with tangent, if you typed in your calculator sine of 60 degrees and cosine of 60 degrees, we would get the same answers that we had in the previous problem. So it says in part B now, use a trig ratio to write an equation and solve for A in the diagram at right. Does it require the sine or the cosine ratio? I would encourage you to draw this on your paper if you haven't done so already. And so in that triangle, this is my angle of reference, and what I'm trying to recognize is I have the side length across from it. This would be the opposite side length, and this is the hypotenuse, and I know the 15 is the hypotenuse because it's across from the 90-degree angle. It's the longest side. So as we defined up above, the ratio that involves the opposite side and the hypotenuse, we use the sine ratio. So when I set up an equation to solve, what I'm going to say is that the sine of a certain angle is equal to the opposite leg divided by the hypotenuse. This looks somewhat similar to the tangent ratios that we've done before, but now we're using this ratio called sine, and so we say the sine of 23 degrees is equal to the leg that is opposite that, which I'm going to call A, as it is in the diagram, divided by the hypotenuse, which is 15. So now, as we've done in previous problems, I'm going to set this over 1, and then I'm going to multiply across, and I'm going to get 1 times A, which is just A, and that's equal to 15 times the sine of 23 degrees. And remember, you can just type this one string into your calculator, 15 sine 23, and it should give you an answer. And when you type that into your calculator, you should get roughly 5.86 units for A. So in this problem, in part B, we used the sine ratio. And the reason, again, that I used the sine ratio is because I had the opposite leg and the hypotenuse. Now that's going to differ slightly for part C. It says, likewise, write an equation and solve for B in the triangle to the right. Well, in this given problem, if 37 degrees is my angle of reference, this side length down here now is going to be called the adjacent side length because it is immediately next to the 37 degrees. Well, Mr. H, what about this side length 8? Isn't that next to it as well? Yes, but that is called the hypotenuse of my triangle because that is across from the 90 degrees. So what we're going to establish now is that the side lengths that we use in terms of our cosine ratio, we can say that the cosine of a given angle is equal to the ratio of the adjacent leg divided by the hypotenuse. So this is another important concept to get down. So within our given triangle, I can say that the cosine of 37 degrees is equal to my unknown quantity b, which is the adjacent leg, divided by 8, the hypotenuse. And again, I'm going to put this over 1 now, and I'm going to solve it. And so I get 1 times b, which is just b when I cross multiply, and that's equal to 8 times the cosine of 37 degrees. And you type that into your calculator, and your calculator is going to spit a number out for you, and it should be roughly 6.39 units. And so this is 2 more new ratios that we've established to help us solve for missing side lengths within a given right triangle. So moving on to problem 5.4, it says return to the diagram from Juanisha's climb in problem 5-1. Juanisha still wants to know how many feet she climbed vertically when she walked up Filbert Street. Use one of your new trig ratios and find how high she climbed. Well, if I want to do that, this again is my angle of reference, and I want to find this side length, the change in y. The change in y is the side length opposite my given angle, and I also know the hypotenuse. I want to include that hypotenuse length and not the change in x because I need some kind of concrete number. I can't have an equation with 2 unknowns like the change in y and the change in x. So I have the opposite leg, and I also have the hypotenuse, and I know that the sine ratio, the sine of an angle, is equal to the opposite over the hypotenuse, and that's why I chose sine, because the sine ratio uses the opposite and the hypotenuse, not the cosine. So as I set up an equation to solve for that, I'm going to use the sine of 31.5 degrees is going to be equal to the opposite length, which I don't know, y, divided by the hypotenuse, which is 100. And so I'm going to put this over 1 and multiply across. And in doing so, I'm going to get y equal to 100 times the sine of 31.5 degrees, which then y is going to be equal to roughly 30.07 feet. So she climbed 30.07 feet vertically from where she started. That would be this distance right here, that vertical component for Juanisha, which we were unable to do at the start of the lesson, but now we introduced this new ratio called the sine ratio, which allowed us to determine that missing length. So now this last problem says for each triangle, decide which side is opposite and which is adjacent to the given acute angle. Then determine which of the 3 trig ratios will help you find x. This is a very, very important problem. Okay, very important problem. Just to help us identify which trig ratio we are going to be using. And so how to start this, I'll help you get going. This is the angle in which we are referring to. So this side length next to it, the one that is not the hypotenuse, we refer to as the adjacent side. And I have the adjacent, and I'm trying to determine the hypotenuse. So which set of ratio, or which ratio includes the adjacent and the hypotenuse? Well, that's the cosine ratio. So the cosine ratio, remember, the cosine of an angle is equal to the adjacent over the hypotenuse. And so what I'm going to do now in this problem is I'm going to set up the ratio of the cosine of 17 degrees is equal to the adjacent leg 3 divided by the hypotenuse, and I'm going to solve. And so your task is to go through each of these problems right here and try and determine which ratio am I going to use, and then how do I set up an equation to solve for it, and then determine the missing length. So I will pause the video and let you work through those to help you edify your understanding. Alright, you can take a look at how you did. For part B, just to set it up again, I chose the sine function because I have two side lengths that are the hypotenuse and opposite, and so sine is the ratio of the opposite over the hypotenuse. So I set up sine of 25 equals x over 9. Solve, and I got 3.80. Something to note on part C. That's a 45, 45, 90 triangle, or it's an isosceles triangle, so both side lengths would be equal to each other. So even though I wrote x equals 1, that is a mistake. That should definitely be x equals 5, as both side lengths should be the same length, since that's an isosceles triangle, so x equals 5. I used the tangent ratio, don't forget about that, on part D, as that is equal to the opposite over the adjacent leg. I do not know the hypotenuse length in that one, nor am I trying to determine that, so I used tangent. And so in the last two examples, again, I used sine and then cosine and letter F, and you can take a look at my work for solving. So the last thing that we're going to discuss today is trig ratios. You have now 3 trig ratios that you can use to solve for missing side lengths. And these, ladies and gentlemen, are super, super important things to get across. Tangent, sine, and cosine are 3 different lengths that can be used in order to help you to determine missing side lengths. And so all of this is in reference to a angle. So if this is my angle down here, then this side length across from it is the opposite. The one next to it is the adjacent. The hypotenuse is always the side length that is immediately across from the 90-degree angle, or the longest length. But the tangent of an angle is equal to the opposite leg divided by the adjacent leg. The sine of an angle is equal to the opposite leg divided by the hypotenuse, and the cosine of an angle is equal to the adjacent leg divided by the hypotenuse leg. If there were something to draw on your paper today after the work, that would be this box with these ratios. Tangent, sine, and cosine are what we call trig ratios to solve for missing side lengths and angle measurements in any right triangle. So, as always, if you have more questions, stop by my office hours. Otherwise, stay safe and stay healthy out there, and we'll talk soon.